Alright, hi y'all. Today, or I guess we're gonna make another video here. This is over spring 2012 and exam 1, question 1, again, another Poynting vector problem. Now this one is a little more difficult, I would say, because it has, E parts. It has 5 parts to this. The good thing is they actually give us, E and H. That's pretty good. But we have to, try and decipher what the heck this is talking about. Right now we're in the, it looks like the rectangular coordinates because we're going through a square. We're also giving x hat and y hat. That's something I usually I've made a habit of myself is to make sure to understand which coordinate system we're in. But anyways, let's read this. So consider a cubical surface shown below. All of the 6 faces of edge length A. It's important because a lot of the times when you're calculating complex power, this is equal to the surface integral of the complex or the Poynting vector dotted with the normal vector with respect to the surface. And a lot of the times you end up having to multiply by the area. And for us, the area is, of course, a times a, just a squared. Anyways, it says of edge length a of the cube are perfectly conducting except the top face. So the top face has fields in it. So we only see fields here. There are no fields anywhere else. It also says the top face at z is equal to a, important, very important here. We will eventually have to plug in a for z, is described by 0 to a and 0 to a. Note 0 to a, integral from 0 to a. So it'll be dx dy for our surface integral. On the top face at z is equal to a, there exists the following set of fields. So at z is equal to a, we have these fields. Cool. So it says first, find the instantaneous power, P of t, entering the cube through the top face. It says entering. Okay, well, instantaneous power, let's figure it out. What is the equation for instantaneous power? Well, that's going to be, you have your instantaneous power. This is going to be the integral of the surface. Remember, power, just like complex power, we're taking a surface integral of the, for instantaneous power, we, in circuits, P of t is usually equal to I times V. Okay, and of course this is in what? Watts or volts per amp. Okay, well that's good to know because this is very similar to this one. And except we're going to be taking just the magnetic field crossed with the electric field. And of course we have to dot it with our normal vector with respect to S, the surface. Now what is our normal vector? It can't just be in. Let's reread the problem. It says, find the instantaneous power entering. Okay, so let's look here. Entering the cube through the top face. Through the top face, entering. So would it be going from this down to up? Well, that would be leaving through the top face. Entering through the top face means it hits it first. So in which direction in the z coordinates is that going? Well, that's going in the negative z direction. Okay, so that means in is equal to negative z hat. So here what we'll plug in is negative z hat. Now we need to figure out E crossed with H. Note we are not doing the conjugate for instantaneous power in the time domain. This is going to be just E crossed with H. Again, you'll notice when you're doing power, complex power especially, in circuits 2 or circuits and systems or any power course, power, you'll see a lot of this as, I believe, I squared RMS times Z conjugate of the load, or something like this, something of this nature, like V squared RMS over Z conjugate of the load. This one I definitely know. We use this so much this last exam for circuits and systems. But in complex power, you take the conjugate. Instantaneous real power. We are only worried about the real components. In our case, we don't have to worry about the conjugate. Anyways, let's find the cross product. So, remember, we're in the rectangular domain. So x hat, E has an x hat. We write cosine omega t sine pi x over a. H does not have anything. It has a y component though. E has 0. H has sine omega t plus pi over 4 sine of pi x over a. All right, and then the z component is 0 and 0. A little trick, maybe not a trick, but something for understanding. Whenever you have two fields that are perpendicular, that are in, x and y coordinates, I'll draw this out for y'all. Let's say this is z. If we have some, magnetic field, which I'll draw in white, it's something like this, and it's in the, what this is showing is it's in the, let's say this y plane, just like this one we have here. And see if I can draw this pretty well. And then we have another in the what? The x plane. Where now we have an electric field in the x plane. When you take the cross product of them, so we'll say this is E, and we'll say this is H. When you take the cross product, they go in the direction, and remember, if you do your right hand rule, they'll go in the direction of Z. X, if it's X, Y, X crossed with Y, you'll end up getting a Z hat. Only a Z hat. If it's purely X and purely Y. Now, if your like electric field is a function of, or maybe not a function, but has, X hat component and Y hat component, it could be a little bit of both. It could end up being, some form of YZ hat in the YZ plane. So this might be easy to see. You have your X plane, Y plane, you know it's going to be a function of Z only, so you really just evaluate the Z hat. So we'll say E cross with H in the time domain again is equal to Z hat cosine omega t sine, and we're doing two sines, so let's just make it right away. Sine pi x over a squared, of course, and sine omega t plus pi over 4. Okay, so all I did was multiply, put the z component there, and now we have to take our surface integral of z hat cosine omega t sine omega t plus pi over 4, sorry, times sine squared of pi x over a. And remember, we're dotting this with the negative z hat component, since that is the direction that our instantaneous power we're looking for. So now, again, when you dot product, we take out the normal vectors, but remember we have a negative, so we'll move the negative to the front so we don't forget it. And now we can't really take a surface integral. We kind of don't know anything about this. So what we do is we go and take a double integral from where to where? Well, remember from before, we have our bounds here. 0 to a and 0 to a. So we take our integral from 0 to a, 0 to a, of what? Cosine omega t sine omega t plus pi over 4 sine squared pi x over a. And then what do we do, though? I mean, this is kind of weird. Remember, we also need to drop that negative, sorry. It's kind of weird. Well, remember previous videos, in the cylindrical coordinates, we put this rho d phi. In rectangular coordinates, we don't have to worry about that Jacobian. So all we do is put dx dy. Remember, this is rectangular, not cylindrical. So now we look, which function here is a function of x? That's not a function of x or y. That's not a function of x or y, but this is. Okay, so what we can do is we can rewrite this negative cosine omega t and move everything out. Maybe it'll look a little nicer for us. This is just for extra work, by the way. You don't have to do this if you know how to take integrals. 0 to a, 0 to a, but this helps me, make sure I'm not making any mistakes that will cost me, like 2 points. I'm not trying to lose 2 points off a silly mistake. dx, dy. Now we evaluate the outside first. So you take this one and this one, evaluate at y. There's no y's, so really you're just integrating 1. And you get what? Y, or you get a. Right? You integrate 1 with respect to y from 0 to a. This is equal to y evaluated from 0 to a is equal to a minus 0 is equal to a. Okay? So now we get negative a cosine omega t sine omega t plus 4, or plus pi over 4. And then now you have the integral from 0 to a of sine squared pi x over a dx. All right, so now you have the integral of sine squared pi x over a. This is a tough one. You have the sine squared. What is that? Sine squared. Oh, man. So what we end up doing here is you take this integral, and I believe we're given calculators. If your calculator can do integrals, just plug in a for 1, so we can let a equal 1. And what you get is you end up getting, this gives you 1 over 2. So what we do is let a equal 1, just replace 1 with a. Should give you the right answer. What I'm trying to say is this integral here will give you a over 2. So now what we have is negative a times a over 2 cosine omega t sine omega t plus pi over 4. And then you, of course, put negative a squared over 2 cosine of omega t sine of omega t plus pi over 4. I believe we're given calculators, or you can bring your own. So I mean, just do the integral on your calculator. You don't have to know how to do any integrals here. And this is the instantaneous power in the time domain. So that's what you should get for part A. Now, let me make sure that's right with the answer choice here. So negative a squared over 2 cosine omega t sine. Okay, we're good here. And it's in watts, remember. So now, what do we have next? The next question asks, find the complex power. Okay, this is where our bread and butter is. This is what we've been doing all, practicing this so much. Complex power through the top face. Again, through the top face. So this will be negative z hat. Be very careful with the wording. So part B. So we need PC through top face. This means negative z hat. So what is the complex power? Well, complex power is, it's still the same surface integral, but now we're taking it in the complex domain. If you want to think phasor domain, this is not in time domain anymore. It's frequency domain kind of area. So now, I guess not frequency domain, but it's just not time domain. So we're kind of in phasors. So now we have times what, negative z hat. No, that's our norm, our normal vector, ds. And if you want already, you can do the double integral from 0 to a of s times negative z hat, just so you remember this is dx dy. Okay. So now we need to find the complex Poynting vector. So what is that? What is this? Well, we've been using this all semester, or I guess for the first 2 homeworks. This is equal to 1/2 E cross H conjugate. Now remember what I said before. Whenever we're in the complex plane and we're using complex power, we have to use conjugates. I believe, yeah, like complex power is equal to V times I conjugate, right? For doing AC components and stuff like that. That's kind of where this is going. E is, your voltage, H is your current, so 1 over 2 VI conjugate. So that's how we're doing it here. And of course you get this 1 over 2 because we're in RMS. But that's besides the point. We need to find E, and E as a function of x, y, and z, no time. So what was our E before? Let's go back up here. E was cosine omega t sine pi x over a. Okay, so E in the time domain is equal to cosine omega t sine of pi x over a. Okay, well, we don't want any times, so this becomes what? Well, this should become e to the j 0, because we have no phase shift. So this is equal to e to the 0 is equal to 1 is equal to sine pi x over a. Now h in the time domain is, let's find it out here, sine omega t plus pi over 4. So we do have a phase shift. We need to remember this. Sine of omega t plus pi over 4. And then same thing, sine of pi x over a. You use Euler's identities again, and this becomes e to the j pi over 4. Okay, you just take your phase shift, e to the j phi. Okay, hopefully we remember that from, I think, like the first homework. If you need a refresher, just go back over the first homework, over the first couple of notes. It goes over it really well. So now what we need to do, hold on, sorry. Sine omega t plus pi over 4. Oh. I'm sorry. This is not sine. We need to make sure and change it to cosine. So, because, cosine is your IEEE standard. So this becomes what? Cosine omega t plus pi over 4 minus pi over 2. So this is cosine omega t minus pi over 4, because pi over 4 minus pi over 2 and pi over 4 is 2 pi over 4, negative pi over 4. So then this becomes ej negative pi over 4 is h. So h in the phasor domain is e negative j pi over 4 sine pi x over a. So then, what do? Well, let's rewrite this. This is just sine pi x over a. H of x, y, z is equal to e to the negative j pi over 4 sine of pi x over a. And now we have to take the conjugate. H conjugate is equal to e to the j pi 4 sine of pi x over a. So e crossed with h. I hope y'all saw why I took, instead of sine, we go to cosine. I hope y'all saw that. Again, it's just because we want to be in that IEEE standard. We want to make sure we have cosines, not sines. So what we do is, to go from sine to cosine, we minus the phase shift by pi over 2. Now, e crossed with h, not cylindrical, rectangular coordinates again. X, does e have an x component? Well, let's see here. Wait, did I skip over that? Hold on. Okay, e has an x and h has a y. So e should be x hat and h would be y hat. Sorry about that. So e has an x hat, which is sine pi x over a, 0, y. This is 0 again, because e does not have a 0 or a y component. And then this should be e to the j pi over 4 sine of pi x over a. Z is 0 and 0. Remember before, when we take the cross product and it's going perfectly in x and y only, we know it's going to be a z component. So we know, especially when you have nothing else, you have all these are zeros, it will always be a z component. So e crossed with h conjugate is equal to the z component of e to the j pi over 4 sine squared of pi x over a. And then that's it. You just multiply those two. No other components. Okay, and then we can rewrite the rest. S is equal to 1/2, so we put 1/2 out in front. So that should be the Poynting vector of our E and H in the phasor domain, remember. Now what we need to do is we need to find the complex power. So complex power is equal to the surface integral, or remember from before, we go from 0 to a and 0 to a, the double integral of our rectangular component. Let me make sure real quick. Oh, wait. At z is equal to a. Did we have a z here? No, we didn't. Okay, then yeah. I almost forgot here. If we have a z, we need to replace it with a. Luckily, we haven't had any z's, so it doesn't matter. But now we have, double integral of our Poynting vector. Remember z hat e to the j pi over 4 sine of squared pi x over a. Okay, and remember we dot it with the negative z because we're going through the top. We're going from top to bottom. And then dx, dy, we need to have two, variables we're taking with the integral with respect to. So now what we need to do whenever we take the dot product, we cancel out the normal vectors and we take the sign. Let's just move it to the front. Don't worry about it now. So now we do the complex power. Are there any variables y in this equation? There are not. So what we do is we can take everything out. We get negative 1 over 2 e to the j pi 4 over 4. We'll keep the integral, like here, 0 to a of sine squared pi x over a dx, integral from 0 to a of 1 dy. So this is now equal to negative 1/2 e to the j pi over 4 times the integral from 0 to a of 1 is y. Then you plug in a for y, you get a. So you put a here. Now do the integral from 0 to a sine squared pi x over a dx. Remember from before, we use our calculator here. Negative 1 over 2 e to the j pi over 4 a times a over 2, which is equal to 1 over 2 e to the j pi over 4 a squared over 2. I guess we can put a squared over 4. And don't forget your negative. I forgot it here. There we go. So this is equal to negative a squared over 4 e to the j pi over 4. Something else you could do is, if you're not sure whether you should finish out, I guess, simplifying this, because e to the j pi over 4 using Euler's identities, cosine pi over 4, which is root 2 over 2, plus j sine of pi over 4, root 2 over 2, so you'd get root 2 over 2 plus j root 2 over 2. Then you do all that stuff, but if you're not sure, I would say to do it just in case. But I mean, it says here in the answers, he left it as is. So now part C. What does part C ask? But this would be your answer here in volt amps. Remember, complex power is in volt amps. So that's part C. Or that's part B, sorry. Part C is asking for the time average power entering the cube through the top face, we're still negative z, by using the complex power. What the hell does that mean? What does that mean, guys? Well, time average power. That's going to be power in watts. Time average power is in watts, okay? Remember that. So, time average power. Usually in power settings, if they ask for power, they mean the effective power or the real power. The reason for this is because in power, power industry kind of standards, we're not looking for VARs. VARs don't affect the amount of real power or real work that can be done. I remember from, I think, physics, work is equal to the integral of power with respect to time. This is not, oh, this is not the complex power, P plus JQ. This is only P. So when they ask for the time average power, they're literally asking you, what is the power in watts? This is very important. Time average power in watts. What does that mean? Well, what this means is we're looking for the real power of the complex power. So we want it'll look like this, by the way. Sometimes they'll ask for it in this. This is real power. Or this is time average power. Well, this is equal to the real component of the complex power. The real component is equal to, remember how I said before, the Euler's identity of our complex power. This is equal to negative a squared over 4 times, what is the real component of, Euler's identity? Well, that's cosine of our phase angle, pi over 4. So what is this? Negative a squared over 4 times, what, root 2 over 2. So this is negative a squared over 8. Negative a squared root 2 over 8. And this is in watts. Do not forget your units here. Part D, I believe it asks for the vars. Let me see exactly how it words it. Yeah, find the vars entering the cube through the top face. Again, through the top face. If it said instead on this one, for whatever reason, it said coming out of the top face, we just take the negative of it. So we want vars, say VRS, is equal to the imaginary component of our complex power. Is equal to negative a squared over 4, because this is the magnitude, and then times j sine, or really we don't have to put j because vars don't have that j part. Your imaginary is already taking care of the j. So then we do sine of pi over 4. Well, look at that. You have the exact same answer. Over 8. Yeah, 4 times 2. This time we're in vars. So our magnetizing vars. And this is negative, so you will have a capacitive load. So it's going to be, I believe, delivering vars. You have like your capacitive banks and stuff like that. You're going to be delivering, uh, you know, reactive power or whatever. Now we have part E. Part E here says find the time average power. Again, remember, you see this time average power in watts. Entering the cube through the top face, so we're still negative z hat, by directly taking the time average of your answer from part A. Okay, so taking the time average. Shoot, what does that mean? Well, to take the time average, and remember, part A was asking for the instantaneous power. Instantaneous power. This is part A. Part A was asking us for the instantaneous power. We're going to have to take the time average of the instantaneous power. Well, what exactly is instantaneous? What is the time average instantaneous power? Well, what we're going to have to do is to find the time average. Do we remember what the root mean square is? This is literally root, mean, and square. This isn't exactly what we're doing, but it'll make some sense. In the root mean square equation, you have to take the time average, meaning you take from calculus, actually, I remember here, from calculus, you take 1 over b minus a, the integral from a to b of your, instantaneous power with respect to time. Now, in our case, a is equal to 0, b is equal to the period. So what we have is 1 over t, the integral from 0 to t, of the instantaneous power with respect to time. This is what we need. So this is the equation we're going to use to find the time average of the instantaneous power used in part A is literally what it says. So let's plug this in. So 1 over t. I mean, what's 1 over t? Well, we have to think of 1 period. Okay, so what are we going to be trying to do? We'll leave this as 1 over t, integral from 0 to t, and then instantaneous power. What do we have in part A? I'll just copy this here. Is this it? Yeah, that is. Okay. This is definitely a longer problem. We're 30 minutes already, and I've been working pretty quick. I'm just showing all my work in the exam. Usually I don't. I just do what I know. But, ooh, this is looking kind of ugly. We might have to do an integration by parts, and no one wants to do that. First thing I noticed is we can take this out because it's not a function of time. But yeah, I don't want to have to take an integration by parts here. So what we will end up doing is we will use trig identities to get this into one term. Now, what do I mean by that? Well, what I mean by that is we can use the trig identities given in the question to solve this. So the first thing I'm going to do is use, I'm going to change sine omega t into a function of more or less cosine. So omega t plus pi over 4 is equal to sine of A, sine omega t, times cosine of B, cosine of pi over 4, plus cosine of A, omega t, times sine of B. This is one of the helpful identities they give at the very beginning. And now what does that equal? Well, this is equal to root 2 over 2 sine omega t plus root 2 over 2 cosine omega t. Well, that's helpful. We expanded this, and now what we need to do is we're going to plug this back in for, we're going to plug this in for this here. So this is equal to, and I'll put this in quotation marks, that way from now on I don't have to rewrite this. This is cosine omega t times root 2 over 2 sine omega t plus root 2 over 2 cosine omega t. And it looks like we're going to be able to multiply these together. I believe that's what we're on the track of doing, and I think so. Yeah, we can do this here. Equal to root 2 over 2. Let's see, we'll take the root 2 over 2 out, and what we'll get is cosine squared of omega t plus sine omega t cosine omega t. And now we have actually the negative a squared over 2, so this portion becomes negative a squared root 2 over 4. And we'll do this, we'll drop this down. But now what else do we do? Well, we also know from other trig identities that cosine omega t times sine omega t is equal to 1/2 sine of 2 omega t. There might be a different way we can do this. If we scroll up, there should be something here. Okay, sine of x plus y and cosine of x plus y. Do we have any of those in there? I think we've already gotten rid of that. Yeah, okay, so yeah, so what we would do is we would use that other trig identity that I just said. This is cosine of omega t, sine of omega t is equal to 1 over 2 sine of 2 omega t. Now I'm looking back at his work. Let me see how he does this. So he took out that cosine squared plus cosine omega t sine omega t. So yeah, this is where he gets, and then he just skips to cosine squared omega t cosine pi over 4. Yeah, I have no clue where he's getting that from. That literally makes no sense. So I'm just going to show you all the steps to this. There are a couple extra trig identities you'll need to know. This is one of them, and then another one is cosine squared. At least this is the way I would do it, knowing my trig identities, but that's definitely, you shouldn't have to need to know this to solve this. Like, I don't know why he did something like this. This is weird. But anyways, we plug in our values, cosine omega t. Oh, well, literally they're already plugged in. Yeah, so now you'd use this. and then you plug it into the equation. And now from there, we can simplify some stuff. All right. Yeah, okay, this is a little ugly, I'm sorry. Yeah, okay. This is definitely ugly. I don't like this. I'm gonna leave this here out for now. Remember, we have to take the integral of 1 over t of this. So we're gonna do, I mean, I guess we could just take the, I guess we could just take the integral of it straight away, huh? Yeah, I think we can. Something I would like to do first, though, is probably, let's see, so we can factor out a 1/2 also, times 1 over 2, and then do sine of 2 omega t. What I did here was I added these, sine of 2 omega t plus 1 plus, or I'll even take out the, since they share a common denominator, 1 plus cosine of 2 omega t over 2, they share a common 2 denominator, we can split them up over 2. And you can factor out the 1/2, and then you'll get what I'm about to get here, plus 1 plus cosine of 2 omega t. So then this is equal to negative a squared root 2 over 8 times the integral, remember, 1 over t, and t is just some time period. In our case, it should be, let me make sure, let me see if they gave us anything here, like an omega or anything, because t is equal to what, 2 pi f is equal to 2 pi over omega. This is just a full circle, right? So you have 360 degrees. Yeah. Okay, well, let me check, because I think he goes from this step just straight to the answer, because he takes the time average, or the 1 over t integral from 0 to t of cosine squared omega t, which is obviously 0. Um, or, no. Yeah, it's 0. Yeah, so you'd get like 1 over t integral from 0 to t of sine of 2 omega t plus 1 plus cosine 2 omega t. And we know the integral, remember the time average of sine and cosines are always 0. And then we have this with respect to time. So then what we get is equal to negative a squared root 2 over 8 times 1 over t times t integrated from 0 to 2, or 0 to t, sorry. And we know this part comes to t, so we can cancel this out, and this is just equal to negative a squared root 2 over 8. There we go. Okay, that's how we did it. And this was the time average power and instantaneous power. All right. So if you notice, though, this is the same answer as what we got. At least it should be. Yeah, there we go. Here in watts here. This is the same answer that we got. Okay, so how do I, one thing to notice is, how do I know the integral of sine omega t, or the time average integral, I mean, the time average of, 2 omega t is equal to 0. How do I know that? Well, if you know, remember from circuits 2 in power, the reason we take RMS is because we cannot state what the average of sine and cosine is. What we can, it's 0. That's why we do this. We use RMS because we want to find a very helpful way to model these voltages and currents in terms of a different kind of quote unquote average, instead of using the actual average. So this would be like RMS, but actual average is here at 0 for cosine and sine. So you can set those for the time average, you can set them to be 0. And of course, the integral of 1 with respect to t is just t evaluated from 0 to t. Period is the period. So then you multiply 1 over t to t period, and those cancel out, and you get this. You did not need this. I was trying to think of maybe they gave us a frequency something, but no, they didn't. So yeah, this was definitely a longer problem, especially if you're going to show all of your work. If y'all had any questions, please let me know. And again, thanks for watching the video here.